So let's look at some examples of how we can use spectra as a type of fingerprint. So for instance, if we look at the hydrogen atom, now the more complicated the atom, the more complicated the element, the atom is, the more complex the spectral lines can be. So the good thing about hydrogen is that hydrogen has only one proton in its nucleus, and if it's neutral, hydrogen only has one electron. So earlier I was talking about kind of the energy levels that an electron can hang out at, and so this is what we're looking at here. We're kind of from the bottom to the top. This is increasing energy. And I kind of think, actually it's not only, I kind of almost think proximity to the nucleus down here. I don't know if that's as much, but so yeah, we call these specifically Balmer lines. So an electron, for instance, can fall from this level 3 to this level 2, and if they do so, if it's falling, it will emit energy at that wavelength. Okay, if it falls from here to here, it will emit light at this wavelength. Okay, you get the idea. These would be transitions. Falling from here to here, notice that what's happening, the wavelength is a lot longer. You see that? If you compare, 18,751 nanometers to 656.3 nanometers. This is a longer wavelength of energy. Over here, we have these long transitions, and if it's a big old transition, then there's going to be a lot of energy, and a lot of energy associated with the shorter wavelengths. Okay? Does that make sense? Now, one of the things, just to kind of mention, you see this ionization. At some point, electrons can actually get so much energy, or they ultimately are removed from the atom. Removed from atom. Because they got too much energy. Okay, electrons are removed from the atom. We call that ionization. So these are what we call Balmer lines. I mentioned these are of course you guys know a meter is a length, right? And nano is a prefix, meaning 1/1,000,000th of. So, all right. So specifically then, do you see where now we're looking at some Balmer lines here? This is the fingerprint or the stellar, well, sorry, it's not stellar. This is the fingerprint for hydrogen. Okay, and you can match up the transitions. Okay, that's that transition from energy level 3 to energy level 2. The greatest transition is right here. Okay, does that make sense? Yeah. Now, these over here, this set over here, where on the previous slide I said that it was at shorter wavelengths, actually, if we could see those, that would be over here. This segment B, these lines would be over here. Okay, they're just, that's not the part of the emission spectra we're looking at. And these lines, longer wavelength, would be over here. Does that make sense? Sorry, over here. We'll call those C. All right. So, now notice that now we've gone from bright line spectra to this is the dark line spectra. So this is Kirchoff's third law. Remember, this happens when, I'll go ahead and draw my energy diagram, when dark lines are created as electrons are promoted to higher energy states. And when they do that, they take in a little bit of energy, and that energy corresponds to these little dark lines. Now, one of the things that I think I would have changed about this figure is, instead of, if this is dark line spectra, we should show the arrows going up instead of down. because it's as the electrons go to a higher energy state that a certain amount of energy is absorbed. But can you see where if you look at this spectra, the dark line spectra for, again, hydrogen, can you see where it's kind of the negative of hydrogen's bright line spectra? Same location for those spectral lines, but now they're dark lines because energy is being absorbed, absorption lines. So this says, I make notes to myself so I know I need to be sure and show you this. So this is a good one. Let's see what you think about this one. One of my favorites. All right, so we have a continuous source basically coming from a star, white light from a star, and notice that if you these are photons of different colors, and it's being gathered by the telescope. So down here, our visual spectrum would look like a continuous source, and our graph would look like that. All right, now what if we put our telescope not in line of sight of the star? I know that's kind of odd to think because stars will shine in all directions, but let's just say that we are somehow out of the loop of white light coming from that star. You can see that that telescope has nothing down here. Well, let's go ahead and let me put the telescope, go back to telescope 2. Let's go ahead and add a gas cloud. All right, so isn't this cool? So this gas cloud then has atoms, and around those atoms are electrons. And specific to what element those atoms are, the electrons are going to rob some of the energy at particular wavelengths of that continuous source. And notice that they're showing that those wavelengths being kicked out of the stream of light coming to the telescope. So what we see is, instead of the continuous source we saw before, we see dark lines. See, I'll go ahead and remove the gas. Now add the gas. Isn't that cool? So this would be Kirchoff's third law. This would be absorption line spectra. Now let's go ahead and look at telescope 1 or telescope 2. I don't know. Let's look at this telescope that's not in line of sight of the star. And now look at what it's doing. It is actually now seeing after the electrons are excited in that gas cloud from that continuous source, the electrons then fall back down to their ground state and they emit out the light at these little discrete energy wavelengths that it was absorbed at. And so we see these bright line spectra, or these emission spectra. Light is being emitted. So I just thought that was cool. I think that was the only one that I wanted to show you. So helium has those, oh, sorry. We saw hydrogen, now this is helium. It's a little more complex. Sodium, not as complex. So these are fingerprints, neon, okay. There weren't very many, there's 3 of those. Let me go back. So there's like a data bank out there, and in this day and age of computers, you can just I don't know, it's not that easy, but you can feed the computer a fingerprint, and it can spit back a potential identity. So I wanted to show you this one. This one's fun. This one you get to play a little detective. So there are 3 elements, and we can put each of these elements spectra down here. So for instance, hydrogen looks like this. We already saw helium. Lithium looks like this. Carbon, pretty. Sodium. Sodium here looks different than the sodium there, doesn't it? Not sure what it is. Neon. All right. So let's just say you go to the lab, and here's our mystery gas, or a gas coming from a celestial object. And we want to know what elements might be in there. So let's just start pulling them up. So for instance, down here then is what hydrogen looks like. Now remember, sometimes our mystery gas actually could be a combination of elements. So, well, that's looking promising. but if you see any lines down here in the element that aren't in your mystery gas, then you know that it's not a member of your mystery gas. So let's look at helium. For example, helium, notice I see this nice strong spectral line here, yellow, and I don't see it up here. And so helium must not be in there. Again, I see helium, a line down here that's not in my sample, so helium must not be in there. Okay, lithium. Again, lithium's not looking too promising. I see a line in lithium that's not in my mystery gas. Carbon, nope, too many lines down here. It's not in my mystery gas. Sodium, now sodium's looking like a potential there. Can you see where all of those spectral lines of sodium, this would be my known sample, match up with my unknown sample? So here we can submit, and yes, we are correct. Sodium is the gas. Well, let's look at let's look at the second sample. Oops. Okay. The second sample looks like this. So let's look at helium. Does it look like it contains helium? Yeah, potentially. Okay. Oh, sorry, that's hydrogen. Let's look at hydrogen. Does it contain hydrogen? These match up. Let's look at helium. Yeah, I'm liking that. But notice if I put the two together. If I put the two together down here in my known, my helium and my hydrogen, notice that bada boom, yes, I get a very good match. Let me see. Let's add lithium. Could it contain lithium too? Because now what I've done is I have extra spectral lines here. All right, let's submit hydrogen, helium, and yes, that is correct. All right, I think I had one more slide to show you. So for instance then, this is looking at potentially, I want to say, information we can get from a star. And this star, by these key spectral lines, we can identify that we have the element helium. We have actually ionized oxygen. This little O plus means that it actually has lost an electron and it's cation. We have helium. This is indicating presence of helium. This is indicating the presence of a neon that's lost 2 electrons. So just to kind of wrap up this section, remember that what appears like actually a continuous spectrum from our sun, actually if you blow it up and magnify it, you can see these spectral lines. And now, in context of what we talked about recently, those dark lines are what we call absorption lines, and they are at particular wavelengths to tell us the composition of our sun. So just to recap again, this was the spectrum we looked at a while back. Okay, with intensity along the y-axis and wavelength along the x-axis. And if we kind of identify regions A, B, C, D, and E, we can say that the continuous spectrum would be dun 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 B and E. Segment A represents an emission spectra, and segments D and C are representing absorption spectra.